Welcome back to example 2. In this video we're going to have a look at how to derive the equation that describes the line that describes the tangent and normal to the function above at any given value of x. In this case x equals -3. So the function at hand is f of x equals x minus 1 times x plus 2 times x plus 3. So in the last video we looked at a quadratic. In this video we're looking at a third order function. Now to have a look at what we're trying to achieve today, if we were to graph this function, what we'd find is this function would look something like that, where the point we're looking at is x equals -3, and so we're looking at the tangent here. Now you might ask yourself, how did I know what this function looks like? Well, the reality is we have calculators, and I had a look at this before doing the question. So what I'd recommend, guys, is whenever you're doing a question like this, it's a good idea to go into the graphing mode of your calculator, throw this in so you know what you're looking for. Alright, jumping straight into it, we're going to use the same steps that we used last time. So step 1, find the derivative. Step 2, calculate the location of where the tangent and the normal touches the original function. Step 3, find the slope of the tangent and normal at said point. And then step 4, find the y-intercepts. So jumping into step 1, we've got f of x equals x minus 1, x plus 2, x plus 3. Alright, and here's where we encounter our first problem. So the problem at hand is, well, we don't have the tools to find the derivative of this particular function yet. So what we're going to do is we're going to go to what we can do. And what we can do is we can expand all of this out, then take the derivative. So what I'm going to do is I'm going to break open all of these brackets and get my fourth or third order polynomial in terms of x cubed plus something x squared and plus something x plus a constant. So doing that, alright, so my derivative, my function f of x, or our function f of x, is defined as x cubed plus 4x squared plus x minus 6. Now we have to find the derivative. So to find the derivative, we'll simply use a simple power rule. Done. Now step 2, we have to find the location where the tangent touches our point, in this case when x equals -3. So doing that, we're going to go f of x, and I'm going to revert back to the original form at the top of the question. The reason for that is purely that it's probably going to be easier to compute the location of f of x given the form that it's in. So we're going to go f of x is defined as x minus 1, x plus 2, then x plus 3. Then letting x equal -3 will be defined as -3 take 1 times -3 plus 2, then -3 plus 3. And here's probably where you realize why I chose that first form. And the reason being is that in the final bracket, -3 plus 3 is simply 0, so everything becomes 0. So our location right there, that is -3 and 0. Too easy. Awesome. Now, moving on to step 3, we need to find the slope of this tangent here. So to find the slope of that tangent, it's simply a case of grab the derivative, f of x equals 3x squared plus 8x plus 1, and then looking at the location x equals -3, the derivative becomes like so. Calculating this, 3 times 9, 8 times still negative 3. Doing the brackets, 3 9s are 27, plus 8 times negative 3 is 24, plus 1, and then it will become 27, take 24, plus 1, 27, take 23, and therefore that's going to be 20, not 20, simply going to be 4. So the gradient when x equals negative 3 is simply 4. Alright, moving on to step 4. We have to calculate our y-intercept. So calculating when this green line cuts the y-axis. Going into that, we're going to find that, or if we remember, y equals mx plus c, and we know that we've got a y value of, say, we've got, what do we find it was? 0 and negative 3, or negative 3 and 0. And m equals 4, because this guy here, rearranging and substituting in the values, c is going to be y take mx, or we can rewrite it as f of x take f dash of x times x. And using these values here, c is equal to f of negative 3 f dash of negative 3 times negative 3, which becomes 0 take 4 times negative 3. And therefore we find that the y-intercept is simply 12. And putting that all together, therefore the tangent is at x equals negative 3. The tangent's going to be y equals 4x plus 12. Too easy. Alright, now that we've got the tangent, let's go for the normal. The normal, remember, being the line that runs, let's get this one, line that runs perpendicular to the tangent and cuts through this point negative 3 and 0 there. So starting from let's say part 3, we'll go the normal is going to be 1 over negative 1 over f dash of x, where x is at negative 3, so negative 1 over f dash of negative 3. And in this case, because we've already got the calculation over here, we can simply go negative a quarter. That was pretty painless. And then going down to step 4, we'll do the same, and we'll go y equals mx plus c. Rearranging, we can write that as c equals y take mx, and then writing it in its original form, f of x take the normal. In this case, it will be 1 over f dash of x times x, or simply put f of x minus, well, it's going to become minus the normal times x. And in this case, we know the values are simply going to be 0 take negative a quarter times negative 3, and that becomes positive, or negative 3 quarters. So in this case, the tangent the normal to the function at x equals -3 is equal to y equals -3/4 x. No, I've done that wrong. It's going to be -1/4 x minus 3/4, like so. And if we wanted to have a look at what that actually looked like, bringing up Desmos, I've already pre-programmed in the graph. And as you can see, the tangent is described by this black line here, and the normal by this green line. And if we go across to looking at -3, we indeed see that the gradient is equal to 4, c is equal to 12, and then the normal slope is -1/4, and the y-intercept is at -3/4. So again, not a very difficult process, nothing we haven't actually seen before, but rather it's just quite long to do. So quite a long process. That's where the challenge comes from in these questions. But again, quite a useful tool to have.